Hi, I'm Nandini Malik, and this is my final course project for Applied Deep Learning. The problem that I was trying to solve was that of detecting cancer in gigapixel pathology images. Human reading is prone to error, and so we use automatic detection as a second opinion. The idea is to assist and not completely replace pathologists. Now, the way I approach the problem, and I will quickly go through the code in just a second, is as follows. We had been given 22 slides and their corresponding masks as TIF files, so I first read in all of them. Then I pre-processed the images, like applied monotone masks, computed percentage tissue, etc. Then I extracted patches from the slides and their masks. Then I assigned labels to all patches by looking at the mask. I then divided my data into training and test. Since the data is quite imbalanced, I try approaches such as oversampling and downsampling to make it balanced. Then I train my model. Finally, I visualize my results through a heat map to see the higher probability regions of tumor. Before going through the code, I will quickly go through the approaches that worked for me and that didn't work for me. First, the approaches that didn't work. So, just using one slide. This gave very inconsistent results because the amount of data was insufficient. Using all slides. Some slides were completely blank and gave no information at all about tumors. Then, using a shallow model. Using a model with 2 or 3 convolutional layers was not able to detect the subtle differences between the tumor and non-tumor regions, and as a result, my F1 score was as low as 10%. Using all the patches from slides. Some patches had no tissue pixels at all, for example the corner patches or patches around the edges. Hence I only took patches which were at least 10% tissue. Then, using just recall or accuracy as success metrics, to reduce the loss, the model just kept predicting either all samples as 1 when recall was chosen or all as 0 when accuracy was chosen. So I ended up using the F1 score, which is the harmonic average of precision and recall, as my metric. Lastly, using a deep and complex architecture with predefined weights. So the one that I was using was Inception v3 with ImageNet weights, which did not really work well with this data set. Now, the approaches that did work were removing blank slides which gave no information at all, removing patches with very few tissue pixels, then upsampling the minority class as opposed to downsampling, which leads to loss of information, then using smaller patches than say 128 by 128 or 299 by 299. This increases the amount of data and captures the more immediate context around the tumors. Lastly, using a deeper architecture with no predefined weights. I used Inception v3 with no predefined weights in conjunction with all of the above pre-processing techniques, which increased my F1 score by at least 40% points. And as one can see, these were the final results on a slide that I had set aside for the purpose of testing. The light pink regions here in the slide are the tumor regions, and the dark areas in the heat map are the regions that have higher probabilities of having a tumor. We can see from both these images that these areas correspond. Now I will quickly go through the code to show how I implemented this. Firstly, after importing all the required libraries, I'm pulling all the TIF files from my drive. Then I'm separating the slides and masks and obtaining OpenSlide objects for each of them by using their paths. Here I'm defining some helper functions to read the slides and return them as NumPy arrays, finding the tissue coverage in the slides, and to apply monotone masks on a given image. Then I'm finally getting the images from slides and masks. Here I'm getting patches from each of the slides. I'm first selecting the slides that are not blank, then extracting 80 by 80 patches at level 7 zoom by sliding a window over them, and only taking them if they are at least 10% tissue. Next, I assign labels to each of the patches. 1 if the corresponding mask patch has at least 1 non-zero tissue pixel and 0 otherwise. Then over here, I'm defining my success metric, the F1 score. Then I'm defining my model, which is Inception v3 with no predefined weights as base and dense layers on top. Then I compile my model with stochastic gradient descent as optimizer and F1 as metric. I then divide my data into test and train. then upsample the training set only. When I fit my model on the training set here, the F1 score comes out to be high, but this is mainly because my training data is really balanced. But when I evaluate the model on the test data, it comes out to be 50%, which is still 40% points higher than what I was getting when I use the shallow model with no upsampling. Then I test my model on a test slide that I had set aside by predicting each of its patches. By visualizing the results, we can see that the heat map corresponds with the tumor regions in the actual slide. I tested it on another slide and found the heat map to correspond with the actual tumor areas here as well. Lastly, I want to talk about the challenges with the approach that I took and further improvements. Firstly, the oversampling technique does make the dataset balanced, but still doesn't help the model learn much to distinguish between the two classes because the samples are simply duplicated. One could perhaps use SMOTE or image augmentation for better results. Probably using a different architecture like VGG with a different choice of optimizer could yield better results. It is all trial and error. Possibly taking different patch sizes would have helped. We could also try to make the tumor patches lighter so that the model is able to detect the differences between the two classes by the RGB values. And of course, getting more data, which can really help building a much more accurate model. And with that, I would like to conclude my presentation. Thank you.